Moving on to question six, it reads that suppose U is an infinite universal subset, and A and B are infinite subsets of U. Answer the following questions with a brief explanation. A reads that it must AC be infinite, which means that everything that's not an A that's a universal subset be finite. Um, I said it's false due to all the subsets are infinite, so obviously everything that's not an A and everything that's not a B also must be infinite. Um, that's what I got, and it's what makes sense to me. But there's a couple different ways you can answer it too. Like if like AC was like all even numbers and BC was all odd numbers, it'd still be infinite too. Um, so for B, the union of A and B must be infinite. I said yes, due to how if A and B are both infinite, then the number of elements that are both in A and AUB are infinite as well, which is true. And then C, must A intersect B be infinite? Um, so again, like I said for A, you could technically have the subsets of the universal set A and B be one being positive, one being negative. So it could be false that they're infinite because if there was one had odd, one had even, then that would mean that there would be no intersect between them. So that's one counterexample to that question. So for question seven, it's a little bit of a hefty one. It reads that given that the universal set is equal to all students at university, and then the set D is equal to day students, M is equal to mathematic majors, G is equal to graduate students, let U be equal to 16, cardinality of U be equal to 16,000, cardinality of D equal to 9,000, M 300, G 1,000. Also assume that the number of day students who are mathematics majors is 250, 50 of whom are graduate students, that there are 95 graduate mathematics majors, and that the total number of graduate students is 700. Determine that the number of students who are, and then it's going to ask you for every single problem underneath. So it's a lot of information at once, but basically you just have to boil it down to what your question is. So it's asking for the number of evening students. So this is pretty simple. We know that there is a set U that is all the students in university, and we defined a set D of all the day students. So to get evening students, it would just be all the students who are studying at the university that are not studying during the day. So U minus D. So 16,000 minus 9,000 is equal to 7,000. Pretty simple, right? Moving on to B, it's non-mathematics majors. We can apply the same logic here. We know that we have U, which is all blanketing all the students at the university, and that we have M, which is all the mathematics majors at the university. Now we can say that everybody, U minus M, which is all everybody in the universal that's not studying math, we can say 16,000 minus 300 is equal to 15,700. Pretty simple. So C, it's a little bit different. It's undergraduates, day or evening. It doesn't matter what time of day they're studying. It's just asking for undergraduates. So we know that the number of graduate students are 1,000, so that means that the number of graduate students or undergrads must be 15,000. Just do 16,000 minus 1,000, you get the answer. So for D, it's asking for something a little bit more different, a little bit more complicated. It's day graduate non-mathematics majors. So we can say that can bring this up into two parts. It's asking for day graduate non-mathematic majors. So we can take the intersection of students who are studying during the day and are graduate students, and we can subtract that from day students who are graduate students who are also non-mathematic majors. So we can do 700 minus 50, which we get 650. For E, it's asking for evening graduate students. Again, we know that the number of graduate students is 1,000. It's already defined. And now we're asking for the intersection between D and G, which is day graduate students, and we're just going to subtract that. So 1000 minus 700 is 300. F is evening graduate students who are also mathematics majors. So again, we're going to go ahead and split this into two parts. We know that there are graduate students who are also mathematics majors, so we're going to look for the intersect of that, which was given at 95 right here. And we're looking to subtract that from day students who are also mathematics majors who also are graduate students. And that is given at 50. So 95 minus 50 is equal to 45. And then the last one is asking for graduate evening undergrad students who are also non-mathematics majors. So it's basically for asking for everything not in the day subset, everything not in the graduate subset, and everything not in the mathematics subset, which we can do a couple ways. First off, D would just be equal to U minus D, which we have here. And then we subtract that from the graduate students who are studying versus the day, which is 300. And then we do mathematics intersecting graduate students minus day students minus grad students and mathematics students. So we get 5 here. So the total answer here is 6,965. There's supposed to be a 0 here for 7,000. That's my mistake. But yeah. So 8 is asking for let A be a set 0, 2, and 3, B be a set 2, 3, and C be a set 1 and 4. And let the universal set be A, U is equal to 0, 1, 2, 3, 4. Lists all the elements of, and it's asking for a multiplication. So it's different than just straight up multiplying numbers in the set. What you're doing is actually you're basically foiling out numbers here. So first you start off with the first number. So let's just take the example A. We're going to FOIL this one out to 0, 2. And our first element in the set is going to be 0, 2. You just do the same thing, you move on to 0, 3. Same thing. Once you run out of the first element to FOIL into the second set, then you move on to the second element of the first set. So 2, 2, 2, 3, 3, 2, 3, 3. Pretty simple. It's always going to be, think of this as the number of elements in the set as the number of elements an A times element B, so 3 times 2 is equal to 6. We have 6 elements here. So for B, it's just basically going to be this, but in a completely different order. We do 2 to 0, 2 to 2, 2 to 3, 3 to 0, 3 to 2, 3 to 3. So C, we can actually see it's a little bit different because it's asking for 3 times now. So basically you can use a cumulative property or associated property to say that we can put parentheses around A and B. So we already have A and B. It's 0 to this whole thing right here. And now we're basically going to do 0, 2 times 1. Or 0, 2 add 1 there. 0, 2 add 4 there. And you just keep moving along. So next pair would be 0, 3, 1, 0, 3, 4, and so on. For D, we're asking for the universal subset times the null subset. And that's just basically going to be equal to a null. Null's pretty weird, but basically any time you multiply by a null, it's going to be equal to null. For E, we have the set A times everything not in A that's in the universal subset. So here, A is 0, 2, 3, and then this is going to be basically 1, 4. This whole thing. Because we have 3 elements, 0, 2, 3. We got to remove everything in here that's in A. So get rid of 0, get rid of 2, and get rid of 3. So 0, 1 would be our first one, 0, 4 would be the second one, 2, 1 would be the third one, 2, 4, 4th, 3, 1, 5th, 3, 4, 6. Now F is asking for B squared, which you can basically break down to B times B. So now it's just an easier way. So 2 times 2, or 2, 2, 2, 2, 2, 3, 2, 3, 3, 2, 3, 2, and then 3, 3, 3, 3. That's it. G, it's the same thing, but you're just expanding it out. I actually did it down here for more room. So we have 222. So we have this times that. So 222, 223, 232, 233. And then we move on here. 322, 323. And then move on to the last one. 332, 333. So now you want to H, and you see a different notation here. It's P with parentheses B. This is the power set. So the power set's basically just an expanded version of the set you already have. So if you look here, we have set 2, 3, and we're going to expand it. You have to include the null set every single time in the power set, and then it's an element 2, or set 2 is an element, set 3 is an element, and then set 2, 3 is an element. And then basically you just do the same thing. So 2 null set, 3 null set, 2 comma set element 2. You have to include these parentheses, and you just keep on chugging. So 9 is list all 3 element sets in P and the power set of A, B, C, and D. This one's pretty easy. All you have to do is just basically look at these and form 3 clusters that are individual and unique. So first one, ABC. Second one is ABD. You have to skip C since we already have C here. And then we have ACD, ACD, and then the last one is BCD. So there are 4. The last one is number 10. A person has 4 coins in his pocket, a penny, a nickel, a dime, and a quarter. How many different sums of money can he take out if he removes 3 coins at a time? So, to set A, I define as a number value of all those coins. So a penny is 1 cent, a nickel is 5 cents, a dime is 10, a quarter is 25. And I basically followed the same rules as here for here. So the first set of numbers, or the first set of coins you can have are a penny, nickel, and dime. So that's 16 cents. A penny, nickel, and quarter, 31. A penny, dime, and quarter, 36. And a nickel, dime, and a quarter, 40. You get 4 different sums here. Thank you guys for watching. Hope this helped, and appreciate